Welcome back. So we're going to do problems from chapter 5. The first problem we're going to do is problem 7. There are two forces, so let's look at the questions. So there are two forces on a 2 kilogram box in the overhead view. So I'm just going to draw the diagram. All right, and the mass is given, which is 2 kilograms. And say this is the top view or the overview. So we have this, and then so you have the x and y. That's looking from from the top. So you have let's see, the only one. There are two forces acting on this box. So this is the box, and it's the top view. And F1 is given, which is 20 Newton, and it's pointing in the horizontal direction. So this is your F1. And F1 has a magnitude of 20 Newton, and it's rightward. And the theta, and it's found that the acceleration, this is the top view. So the acceleration is moving that direction. So you have the accelerations here, and the angle is given, which is 30 degrees here. And the magnitude of the acceleration is 12 meters per second. And it's pointing in the third quadrant. And you want to find the second force in unit vector notation, and also the magnitude and angle relative to the position directions. Let's see. You just want to find the second force in unit vector notation, and also the magnitude and angle notation. How do we do this? Let's look at these problems again. So you have the 2 kilograms, box sitting here, and you apply the force that is rightward, but I found that the whole thing is actually moving in this direction. So which means that there's a second force acting on this box, so that the net force is in that direction. Because remember, the acceleration is in the same directions as the net force. So it's moving, the whole thing is moving that way. So where would the second force be, and what is the magnitude? So how do we do this? Again, we realize that you have the net force. The net force, okay, is equal to the mass of the object times the net acceleration. Okay, so the acceleration is right here. So we can actually, so this equation basically can be split into two. One is in the horizontal direction, and one is in the vertical direction. So let's look at this acceleration first. Let's resolve this vector into the x and y and express it in unit vector notation. So you have your A, which has a magnitude of 12, and I'm going to use the small angle notations. In other words, you have to manually put a negative sign in front of the magnitude, because it is in third quadrant. So we know that you have the negative horizontal component, and you have the negative y component of the acceleration. So you have so if this is the angle, so the x component is this, and the y component is this. So you can see that this x component is opposite the angle, so you have to use sine. So you have your 12, and then sine of 30 degrees. And then you have to put a negative sign in front of it to indicate that it is leftward. And then that is your I hat. So this is your x component. What about your y component? Your y component is next to the angle, so that's cosine of 30. So you have your 12, and then cosine of 30, and that's j hat. And again, you have to put a negative sign in front of it, because it is pointing downward. Okay, so numerically, you should have the acceleration, and that is, let's see, so this is -6 I hat, and then this is, this is negative 10.4 j hat. Okay, and that's meter per second squared. So this is the acceleration in the x direction, in the y direction. And now let's go back to this net force. So this net force has ma. So in that case, what we can split into the x and y components. So we can write it this way. So the net force in the horizontal direction has to be equal to the mass of the object times the acceleration in the horizontal direction, and the net force in the y direction has to be equal to the mass of the object times the acceleration times the acceleration in the vertical direction. So let's see what are the net force in the horizontal. Let's say if you have the third unknown force, so the second unknown force. So let's say you have your F2. Okay, and that's say your F2 has F2x I hat and then plus F2y j hat. So in that case, what you can do is that you have the this F1 only exists in positive 20 I hat, and there's no vertical component. So when you plug into this equation, the net force in the horizontal direction you have the F1 and F2. So you should have the 20. So the net force, this you add it together. So you have the 20 plus F2x. Okay, that's your net force in the horizontal direction. So this is this, and that's equal to the mass is 2, and the horizontal acceleration here is -6. So in that case, you can actually calculate your horizontal component of the second force, which is negative 32 Newton. So you find the S component of the second force. Now we're going to do the same thing on the Y component. So when you add these two together, so you have your 0, the first one, and then plus F2y, that's equal to mass of the object times the acceleration, which is negative 10.4. And so your F2y is equal to negative 20.8 Newton. Okay? So you can see that this result is obtained by applying this equation. The net force in the horizontal direction is equal to the mass times the acceleration in the horizontal direction. And this is obtained by applying this equation. So F2y, F net y is equal to MAY. Okay? And so on the left-hand side, you need to figure out what is the net force. So net force in the horizontal direction, the net force in the vertical direction. And that's how you got the this. So in other words, your F2 will have, in unit vector notation, you will have a negative 32 I hat, and then negative 20.8 j hat, and in Newton. Okay, so this is your F2, and that's in unit vector notation. Now, you're also asked to find the force expressed that in angle magnitude notation. So in that case, you need to find out what the F2 is. Your F2 is equal to square root of the horizontal component square plus the vertical component square. So your F2, after you do that, your magnitude is equal to 38.17 Newton. All right. So this is the force magnitude. What about the angle? So to find the angle, plot it on the x and y axis. So you have the negative I component, you have the negative y component. So your force F2 is actually in this direction. So you can define your angle however you want to define it. That's how we define this angle theta. So in that case, the opposite is your F2y. The adjacent is your F2x. So you can calculate tangent theta is equal to, use the absolute value, your F2y. Your F2y, that should be in the numerator. That is negative 20.8. And then your F2x, which should be in the denominator, that is negative 32. So your theta, after you do the calculation, your theta you should get 33.02 degrees. So adding 90 degrees to that, then 180 degrees to that, then you get the final answer theta. So your theta here is equal to 33.02 plus 180. So you should get a value that is equal to 213. Roughly degreOkay, so this is how you calculate. This is how you find the second unknown force. If you know, what is the acceleration, because the acceleration is in the same direction as a net force. Okay, and you have the one force here. The other force we just found that is actually in this direction, and it's not exactly the same as the acceleration. That's because you have the F1 here. So after you sum up both the forces, you find that the final acceleration is the net acceleration is in that direction. Okay, so that's your problem 7. I'm going to move on to problem 29. So let me erase this. All right, 29. Okay, we have a firefighter who weighs 712 newtons. So the weight of the firefighter is 712 newton, and slides down a vertical pole with an acceleration of 3 meters per second directed downward. So the acceleration that it has is equal to -3 meters per second squared, because it says it's moving downward, so you have to put a negative sign in front of it. What are the magnitude and directions of the vertical force on the firefighter from the pole? And you also find the magnitude and directions of the vertical force on the pole from the firefighter. So you can see that this is, we're going to utilize the Newton's third law. The action is equal to the reaction. Okay, so what we have here is that let's draw a free body diagram for this. So this is firefighter, and we know that it has a weight, okay? And the pole is going to exert force on the firefighter. So the force on the firefighter will be upwards, okay? So you have, let's say this is the firefighter. This is the force exerted by the pole on the firefighter, and the whole thing is moving down in this direction. You have the acceleration that's moving down. So in that case, when we look at this free body diagram, there are two forces acting on the firefighter. One is its own weight, that's downward, and the other one is coming from the pole. Okay, and that's we call that FFP. So in that case, we can find the net force. So what is our net force? So our net force here is that upward, so that's FP, which is positive, and then plus the negative of the W, because W is downward, so it's negative W. And the whole thing here, instead of setting it 0, because we're using this, F equals MI, and in the vertical direction. So the net force in the vertical direction will be the difference between the force on the firefighter and the firefighter's own weight. So this is the net force, and the whole thing is equal to MA. So you have your mass M, and your A here is -3 because it's going downward. We don't know about this. You're asked to find, but we do know the weight, which is 712. What about the mass of the mass of the firefighter? If this is the weight on the firefighter, then the mass of the firefighter will just be the weight over G. So you have 712 over 9.8. So the mass of the firefighter is 72.65 kilograms. So we can plug into here. So you have 72.65 multiplied by -3. So you can see that the force acting on the firefighter from the pole is equal to 494.05 Newton. Okay, so that's the answer on that. So you can see that this is a force on the firefighter. And the second part asks you to find the force on the pole from the firefighter. So because like I said, the force on this, so the force on the firefighter should be equal to the force on the pole, but in the opposite direction, because they form a third third force pair. So in that case, you have the force acting on the pole from the firefighter is equal to this P here, based on Newton's third law. So they becomes a force pair. So this one is upward, okay, because we define it to be upward. So in this case, then this one has the same magnitude, but it is downward. So you can express that as this, okay, and that's because they become let's see. So this is basically utilize Newton's third law. Okay, so FPF is equal to FP. So that's basically that. Okay. So this is a simple problem. Let's move on to the next one, problem 34. Okay. All right, problem 34. In the diagram, so let me draw a diagram first. And you have a crate, and a force, and the angle, and the mass. All right, so a crate of mass, M, that's 100 kilogram, and is pushed at a constant speed up a frictionless ramp. And the angle here, theta, is 30 degrees by a horizontal force F. So F, the magnitude is not given, but it's pushing it up horizontally, pushing it up. So you apply a horizontal force on this crate, and the whole thing is moving up. The crate is moving up at a constant speed. So the key word here is constant speed. All right, so you want to find the magnitude of the force on the crate. You want to find the magnitude of the force and also the force on the crate from the ramp. Okay, so this is the crate and this is the ramp. You want to find the force on the ramp on the crate from the ramp. So how do we do this problem? So let's look at this. You have the keyword, like I said, the keyword here is constant speed. When it's moving at a constant speed, so this crate is moving at a constant speed. What does that mean? It means that there's no acceleration, okay? Constant speed meaning the net acceleration, the acceleration is equal to 0. And I use the vector form because the acceleration, now we're dealing with 2 dimensions. So you have the horizontal acceleration and also the vertical acceleration, and both should be 0 because you're moving at a constant, the crate is moving at a constant speed. So the first thing we need to do is that we need to draw a free body diagram. Whenever you have this, this at an angle, you want on the incline, you want to draw a free body diagram directly on the incline, and also you want to rotate your axis. Now, your traditional axis, of course, is rightward, upward. This is your x and y. But now, whenever you're doing this kind of incline problem, you have to rotate your axis so that your new horizontal axis is along the plane of the incline. Okay, so this and this, they are along the same direction. And then once you have your new x axis, then the new y-axis will just be perpendicular to your new axis. So what we are doing here is that you're going to rotate your axis system, x and y axis into this, rotate it so that your x is along this plane and your vertical is actually perpendicular to this. So we'll get back to this, the traditional x and y axis, but then with the new system. So in other words, so let me draw the line. So this is your new x-axis. This is your new y-axis. So these are now our new reference axis. So now we need to draw a free body diagram. So this is the dot indicate the object. We have the force as the rightward, so you can see that it is actually now at angle. So instead of using the original x-axis, your F actually has a component along the new x-axis and along the new y-axis. Okay, how many forces acting on this crate? We know that this one is external force, so that's in that direction. This crate is also at all time experience gravitational force, so we know that it should be perpendicular because it's perpendicular to toward the center. So you have the mg, which is the weight of the crate. So that's perpendicular, okay? But according to the new x and y axis, of course, it's not along the either one of the axes. It's actually off the axis. So we know that when you resolve this factor into the new x and y axis, you will have the non-zero components in both axes. Okay. How many? So we have this gravity. You have the external force. What are the forces? How many other forces are there? There's no friction In this case, there's no friction, so you don't have to worry about friction. What about normal force? This crate is in contact with this incline, which means that it this incline is going to exert the force on the crate, and also the crate is going to exert the force on the incline. So it's very similar to when you have a block on the tabletop. The table is exerting a force on the block, and the block is exerting a force on the tabletop. So in that case, we know that there is a normal force, and that normal force is perpendicular to the object. So you have a normal force here. So now you have altogether 3 forces acting on this crate: external force, gravitational force, and a normal force. So now we are ready to apply Newton's second law, realizing that constant speed, which means that the acceleration is 0, and this is ax is equal to 0, ay is equal to 0. So now we can actually use the net force is equal to ma, so that you should have 2 equations, one in the horizontal and one in the vertical. So let's look at the one in the horizontal. When I say horizontal, I'm meaning according to the new x axis and the new y axis. So I'm going to use x prime and the y prime. Okay. So in that case, how many forces that can be projected along this new x prime? This force is right here. You have a gravity here. No force is perpendicular, so it has no contribution. But we know that this force and your gravity, they're going to have a component along the x prime. So let's find out what that component is. This is your force here. So that this is horizontal. So this theta and that theta, it should be equal to each other. So your F. So this F, if we project it to this, your x prime, the Fx. So let me just, your Fx, so your F here, you have a positive x component and a negative y component. And this is according to theta, and this is your hypotenuse. So your F, if we express in unit vector notation, you should have F, and then you should have the cosine theta, I hat, and then minus F sine theta, j hat. I use minus because it's downward, okay? So this is your F. What about your mg? So your mg, this force you have, so that's say Fg. You should have, so this angle theta and that angle theta, so this is the same angle theta here, okay? So this angle and that angle are the same. So you need to resolve this vector into this. You can see that the gravity will have a negative horizontal component and a negative y component. So in that case, you have your mg, negative mg, and then the x component is opposite the angle, so sine theta, I hat. And then the y component is adjacent to the angle, so you have negative g, and then cosine theta, and then j hat. So you have these 2 forces that all have a non-zero component in the new x and y axis. So now we're ready to find out and use the normal force. Let me just write it down here. So the normal force has zero component in the new x-axis, but then it has the upward or positive component in the y-axis. So now we're ready to actually just add them together, right? So the net force is equal to that. So let's do component by component. For the s component, you add this s component together. So what we have here is that the Fx the net force in the s component is equal to this. You have F cosine theta, and then minus mg sine theta, and then plus 0, because you have no components there, that equal to ma. And it's max, right? But now because ax equals to 0, so you have your 0 here. So what does that mean? It means that your F cosine theta is equal to mg sine theta. So now your F is just equal to mg sine theta over cosine theta. Okay, so now that we can plug in the number, your m is 100, your g is 9.8, and your sine is 30 degrees. So after we do that, you can find that your f here is simply equal to 565.8 Newton. So this is how you find the force. So you can see that just by using the horizontal component, you'll be able to find out the force magnitude already because you have sufficient enough information to do this calculation. Now, you're also asked to find what is the force acting on the crate by this. So in that case, we can utilize additional equation that's in the vertical direction. So let's add all this together. So we have this, all the y components. We add all the y components together and see what we have. So this is positive, so because it's positive, so this is going to be the leading term. And then, so this plus that should give you to give you MA, but because the AY is 0, so that after you add this together, it's going to give you 0. So let's do that. So you have your normal force, and then minus mg cosine theta, and then minus f sine theta. The whole thing is equal to 0. You're asked to find n, so let's see what n is. So your n here is equal to mg cosine theta plus f sine theta. So you have your m, that's 100. You have your g, that's 9.8, and then times cosine of 30. And then plus your f, you just figure out the f magnitude, which is 565. So 565.8, and then times sine of 30. So after you plug in the numbers, the normal force that you should get is 1,131.6 newtons. So that's the final answer here. And the force is this. Okay, so this is a typical problem when you have an object moving on the incline, and then you have to rotate your axis, so and resolve your vector into the new x and y axis, and then depending on whether it's moving with the acceleration or it's moving at a constant speed, then you can apply Newton's first law or second law. In this case, we'll apply Newton's first law because everything is 0, it's moving at a constant speed. So F net is equal to that is equal to 0. So you sum out all the x component and set it equal to 0. Sum out all the y components, set it equal to 0, and then you can calculate the unknown quantity. Okay, so that's a typical problems. Okay.